might do closer to prelims. August, is it? You said, when's yours? End August then. Yours is what? Which part of August? So yours is mid-August. Yours is mid-August here. And then yours would be like either after, like 2 weeks after National Days, I suppose. Yeah. Those who, yeah. And then your prelims will have practicals as well. When is that? That's unnerving. If you're, yeah, that's not possible. Yeah. Any self-respecting school should always have a practical for their prelims, okay? All right, that's gonna be a bit worrying if you don't have one. What? Ah, then suddenly it what the practical is 19. So when is the actual paper itself? Okay, all right. So do you know what you have to do? You have to text me these details. I won't remember it, but it just keeps as a record for me. So both of you, right, tell me what your in fact Joshua and Shasha as well, please text me all your practical prelim dates as well as your prelim paper dates, right? And then for Alvin, what are you doing to prep for your exam? Which one? When are you going to start doing the yearly papers? When is your next HBL? I believe it's 15, 16, 17 July. Okay. Yeah, I have RI boy. Another one. Uh, okay. So basically, I'm gonna make use of that couple of days to go through any of the yearly papers or topical papers that you might have. Right. I'm gonna reserve a timing for you. I believe I want to do on the 15th, because I'm already booked up on the 16th and 17th. So you have to kind of like get some papers done within the week, right? And then I'll see you on the 15th to go through any of the questions that you may have. So you have to quite quickly churn out as many papers as you can, right? Then make use of this 15th of July session, right, properly with me. Is that okay? All right. Text me that you will see me on the 15th of July for HBL. Yeah, text me now so that I'll remember. Okay. Then for you all got the notes, right? Okay, and then for the topics, yeah, we're gonna go into EMI. So let's do a quick roundup on what you have done so far, what we have done so far, or what you're supposed to know so far. We're on chapter 19 now. We're on chapter 19. Sorry, the title of the note says 22. The notes are also online. Hang on, let me just do a quick check. Yeah, there is there. Yeah, chapter 19, right? Electromagnetic induction. Sorry about that. The title, I couldn't find the original file. I don't know how to amend it, so I have to go and figure it out later on. But just strike it off and then put 19 for yourself. We're on chapter 19. We're almost at the last chapter. We're second last chapter already. Right? I mean, just as well because we're already in term three. It's going to take me another 3 to 4 more weeks to finish the last two chapters. Right? So that's why I need to start doing some papers as well, which is why I just texted everyone. Nanhua High paper one due on the week starting 14th of July. Did I say that to you just now? Did you hear me say that just now? Okay. Right. During the June holidays, we tried to revise some things, kinematics, dynamics. I think was there this and this or something like that? Yeah, and then light and lenses. Yeah. So we tried to revise some of these things. A few of the things that we didn't really revise. But I mean, I would say that I still need to figure out what you need, right, as we go along for revision. I don't enforce like, oh, you must follow this program or anything like that. So what we need to do is we need to figure out what you're bad at still. So then I can decide what to do for topical revision, which is why we need to start doing papers, right? It is me. This is me trying to figure out what you need, right? Not me like enforcing like, oh, okay, you know what? Let's just apply a general solution for everyone, right? Oh, you, everyone will be the same, right? All of you are the same. No, that's not true, right? Some of you are better at some other topics than others, right? So we need to figure out what you're bad at, right? Then we can do the targeted topical revision for each of you, right? But yeah, so you have to get the practice done. So my instructions was 14th of July, Nanhua paper one, right? 2024 paper, right? It's the most recent prelim papers, and therefore it will have the most updated content as well, right? Then for some of you, you're not doing nuclear physics at all in your syllabus, right? So for those weeks, please skip the lesson, right? Are you doing nuclear? You're doing nuclear. Are you doing nuclear? You're doing nuclear, right? So you have the two of you can't skip, right? The one over there can skip, right? Don't think that you can skip. So that means that your life is easy. I'm gonna assign you papers during those 2 weeks. Okay, all right. So then we can figure out what you need as well. Okay, the for the IP guys, the aim of the game is to make sure you can go on to JC without or IB without any problems. But it also serves as a kind of like the foundation, right? Should you take higher level physics or H2 physics in JC or IB? I must tell you this, most IP students that go on to JC will suddenly realize that the JAE students, the O-level students that join the JC, the O-level students actually do a lot better and they do a lot faster. They learn a lot faster when they are in JC or IB, right? And that's because for the O-level students, they really have to grind the definitions. They have really have like everything is it's really important. And I think one of the key factors is because the O levels students, right, they don't get their paper back. So they have no idea what they got wrong, which means you got to get everything right, right? Right? There's no margin of error. Why? Because they don't know what they will get it wrong. So they have to really go and grind all the definitions, all the phrases, all the concepts. They keep grinding, 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 right? Okay, right? They do the TYS 2 times over. They do like five, six, seven prelim papers before the prelims, right? Okay, so their foundation is very, very strong. Of course, the idea of the IP program is not that, right? The idea of the IP program is a holistic education, right? As long as you get the general idea. Which is why very, very strangely, a lot of students think that, a lot of parents think that, oh, IP school, like, isn't IP more difficult than O levels? Nah, I don't think so, man. Right? The O level standards is much higher than IP, right? Come on, they do nuclear, no, you don't do nuclear, leh. But then there's nuclear physics in IB, what does that put you? That puts you at a disadvantage. Anyone who goes in from O levels to SJI IB, right, will have an edge over you. There's altogether 4 chapters on nuclear physics in physics in IB. You get what I'm saying? So don't have the misconception thinking that IP is higher standard than the O levels. No, it's actually like the other way around. And in fact, a lot of IP schools follow the O level syllabus. When the O level syllabus had nuclear, the IP schools started to add in nuclear into it. They have to keep up because who are the ones who make the rules? MOE. MOE controls O levels. IP. Who is the one who make the rules? Your HOD sit there one day he decide. I think I want this. I what gives him this random, it's random, right? Isn't it? Like, look at your HOD. Like, think about it. Like, he's sitting there at his work table and then he decides that, okay, you know what? SGIIP, no nuclear. Who gives him the right to do that? Why? Who gives him the right to put you at a disadvantage to all the other students? Right? Think about that. That's so weird, right? I don't know. It's hella weird to me. Anyway, sorry for the rant. Let's start. Okay, so we're gonna do EMI, all right, and alternating current. So EMI is called electromagnetic induction. You might want to write that down. Electromagnetic induction. Okay, electromagnetic induction. What was the chapter before this? What was it called? What was the chapter before this? I mean, we did this in May, so it's been a while, right? We did the previous chapter in May, so it's been a while. So what was the previous chapter called? It was called electromagnetism. You get what I'm saying? It was called electromagnetism, right? So I mean, if you had, kind of like seen the list here, it was called electromagnetism, right? And then yet before that was magnetism. You get what I'm saying? So electromagnetism, electromagnetic induction. Now, electromagnetism, what was inside here? Do a bit of recap. What was inside electromagnetism? Yeah, oh, electromagnetism. Like, what was the first thing you learned in electromagnetism? Correct? No, you learn magnetic fields in magnetism. So what was the first thing you did in electromagnetism? Yeah, right hand grip rule. Right? It's right hand grip rule. That was the first thing. Why is that electromagnetism? Why is the right hand grip rule electromagnetism? Come on. Like, what was the right hand grip rule used to do? Oh, very good. Right, a very direct answer. Okay. Wrong. Wrong hand some more. Oh, you already done this, is it? Eh no. What's your chapter on in school now? Oh yeah, yeah, okay, okay. Now this one is something. This one is for this. Okay. Yeah, anyway, so what's it again? Sorry. Right. Find the magnetic field of a current. Right. Good. So if it's a circular coil, you can change your finger to the current, and then your thumb will represent the magnetic field. Right. So if it's a solenoid, so it's either a straight wire, then the fingers represent the magnetic field, or it's a solenoid, then your fingers represent the current, and your thumb represents the magnetic field. Right. You get what I'm saying? Yeah. Okay. What else do you learn in electromagnetism? What else is there? What? Yeah, left hand rule. That's right, left hand rule. What does the left hand rule do though? Find the force. The force. Okay. All right. So the left hand rule is to help you find the force. So if you had a current sitting in a magnetic field, it will experience a force. Right. So I mean, I'm doing this because I want you to remember that this one, right hand grip rule, has no force. Right. But then left hand rule has a force. Right. And the left hand rule will be you comparing between a current and an existing magnetic field, and then therefore you get force. What was the last thing that we learned in electromagnetism? We're doing a recap, so trying to recap now. What's the last thing? What do you remember learning in the last part of electromagnetism? Okay, what's that whole thing called? Not just the split ring. What's the whole thing called? That thing that the one where we draw. Yeah, it's a DC motor, right? It's a DC motor. So that was the last part of electromagnetism. Okay. Amongst other things, that's not it, right? So if you are doing your own revision, which you should, right? If you want to do a quick flow chart or mind map of this chapter, yeah, please go ahead. But yeah, I guess that would be great. Don't spend more than 2 hours doing it though. Like I want you to do this, okay? If you're revising anything, any chapters here, right? If you're revising any chapters here, and you want to do your own like kind of like mind map and all that, right? For each of the chapter, 20 minutes max. All right? Because that it really doesn't take that long. Definitions, equations, and diagrams for each chapter. As you go through the textbook, you look at every scenario, you look at every equation, you look at every definition. It should not take you more than 20 minutes. Because I don't want you to waste time just flipping through the textbook. That's not studying. That's just called revision. That's why it's called revision. Get it? You're just looking at it again. You got to practice. So the next thing you do after that is to do the practices, right? That's the most important thing. Okay. Right. Then you have electromagnetic induction. So in this chapter, what we're gonna do is we're gonna learn, right, about this thing here, right? Electromagnetic induction, right? This thing here. So the idea here is that you will have a magnet, you will have a coil, and then the coil is attached to a battery, right? If nothing is moving, sorry, did I just say battery? Bulb, magnet, coil, and bulb. What I wanted to say is that you don't see a battery here. There's no battery here. And if nothing is moving, the bulb won't light up. The bulb will not light up. Okay? But once you start moving something, then the bulb will light up. You get the idea? Right? So electromagnetic induction is talking about generating electricity. How do you generate electricity without a battery? No battery, right? Just hand movement, right? And then you can create electricity and then the light bulb will light up. You know what I'm saying? So that's what this chapter is all about. How or why? Actually, it's more like how, not really why. You don't have to care about the why. How do you generate electricity? Okay? Essentially, you get the gist. You don't move, there's no electricity. You gotta get it moving first. right? So that means you have to move something. So if you see a picture like this, and I tell you that, oh, I place a battery, sorry, I place a magnet, I keep saying battery. I place a magnet next to a coil, okay? But I don't move, if I don't move anything, there is, the bulb is off, okay? So the next page, right? We go to the next page. Now it's a unusually big blank page. I mean I didn't know where else to fit this, but I need you to draw something here. So we're gonna draw it together here. We're gonna understand what is magnetic flux first. Now you've done this in school. So what is magnetic flux? Ugh, Thailand. I thought you went to China. You went to Thailand then China. Okay, okay, pay attention. Take down all the notes. Hey, what's magnetic flux? Okay, fine. Right. Okay. So what I'm gonna do now is gonna draw a magnet for you. Okay. Yeah. I'm gonna draw a magnet for you here like this. I'm gonna draw a magnet. So you all draw together as well. Draw a magnet. What's around this magnet? Magnetic field. Okay. Magnetic field. So yes, there's a magnetic field. Right. So we draw a magnetic field like that. Okay. We draw a magnetic field. So some teachers, I'm gonna tell you this. Okay. So some teachers will just tell you that this is flux. Like, the magnetic field is called flux. Not quite. Okay, if I want to be really accurate about this, it's not really true. Okay, magnetic field, right, coming out of the north like this, going into the south like that. Magnetic field isn't exactly magnetic flux, right? Magnetic field is just the field lines that's coming out of a magnet. You want to demonstrate flux, you got to have a coil. Okay, so I have a coil here in case you're wondering what a coil is. Some itchy hands started to play this thing and started to make it out of shape. These people are horrible. Okay, so for those who are online, this is the coil I'm talking about. You realize that I've been using this coil for a while now. Ever since we were doing the magnetism, right? I've been showing you this coil. This is a copper coil, right? Copper coil. Yeah, you all know this, right? Maybe you don't know this, but if you look at this copper coil, it looks like it's bare copper, but it's not bare copper. It's actually it has a enamel coating, so it's an insulated copper wire. Because if it was bare copper out in the environment like this, it would have been oxidized and become copper oxide, and it would have turned green. But the fact that it remains this like copper brown color, right, for so long is because it's an enameled copper wire, so it has to be insulated. As in, like when you create a solenoid, it has to be insulated. When you use a copper coil or you use a coil of wire, it has to be insulated wire. It can't it can't be bare wires. So I'm gonna place this copper coil next to the magnetic field. So you will draw this, right? I don't need to draw very accurately, just kind of like draw a coil of wire. So this is a coil of wire, right? Placed next to the magnet. In case you need a real life example, right? This is how it looks like. I have magnets with me here, right? This is a magnet here, like that, right? It's a magnet, okay? And I place a coil next to it, like this. That's what I'm showing you, right? That's what this is all about. Okay, so I have a magnet, right? And it's facing basically the magnet is facing the empty area in the coil, like this little like area here in the middle here like that. Okay, it's facing the coil there like this. All right, so this is the coil over here, right? There you go. Now, when the magnetic field cuts, right, or let's say enters into that surface area. So this surface area I'm referring to is the oh gosh, bad color, but okay, never mind. Right, it's the inner surface area. It's like this. We're talking about this empty area here. So when the magnetic field lines goes into the area of a coil, that's called flux. Right. So flux is generally understood in a professional way, right, as the magnetic field lines that is cutting the area of a coil. Right. Flux is the magnetic field lines that is cutting into the area of a coil. Now, this area is not the wire's area, it's the empty area in the middle here like this, right? So if a coil like that, okay, then the empty area in the middle, the magnetic field goes in, and then that's called flux, right? Without the coil, this is called field lines. Just the coil alone, it's just a coil. With the coil and the magnetic field, right, going into it, that's called flux. Okay? So the idea here is how much flux is there. Like, there's a way to quantify it. There's a way to quantify it, but it's none of your business. Right? It's not yet, right? So you will be doing this later on in JCIB, right? But yeah, you don't have to care about like how do I quantify it. You just need to know that flux can be less, can be more, right? I mean, if you move the magnet away, then it'll become less. If you move the magnet closer, then it'll be more. Can? Right? Okay, you get the idea. Good. So that's flux. Right? So how then do we generate electricity? You notice this, right? If I don't move it, there's no electricity generated. Only when I start moving it, right, then it will start generating electricity. So which means that if you don't move the magnet, right, nothing's gonna happen. There's no electricity that's gonna be like created inside the coil. We're trying to create electricity in the coil. We're not trying to create electricity in the magnet, right? That makes no sense at all, right? So we're trying to create it in the coil. I mean, I say this, but yes, over the years, I've had a lot of students who have this misconception thinking that, oh, we're trying to induce some electricity inside the magnet. No, that's not what we're trying to do. Okay? So in the next page, let's jump right in. Faraday's law, Lenz's law. Let's quickly go into it. So these are like the two most important laws, and you will be quoting these two laws every time you get a question regarding EMI, right? Like these are the two go-to laws that you use. Okay, so let's go through this. Now I'm gonna spend quite a bit of time today's lesson going through this page and probably like something in the next page. But that's all for like pretty much today. But you would have to draw a lot of things. I didn't prepare for that. You can either use the page before this to draw stuff that I mentioned later on, right? Or you can just take some more paper and draw stuff. Can you help me pass paper around? Okay. So yeah, just take note of this. So right now I'm gonna ask you this. Do you see the magnet here? Do you see the coil here? My first question is there flux? Is there flux? Why yes? Exactly. Direct answer. Because the magnetic field lines are going through the coil, right? I mean, it's like if I have a coil here, then the magnetic field lines are just going through the coil like that. So is there flux? There is flux. There is flux, right? I mean, it's close enough. There is flux. You get what I'm saying? Right, there's flux. Now, for those who are not sure, because some of you are like um like quite new to me as well. What is this box here? Do you remember what I said about this box during electromagnetism? Was that? Yeah, pretend it doesn't exist, right? So it's like I said in the previous lesson. Just imagine that it's a toilet roll, right? It's a toilet roll. It's just a holder. It's just a holder. The reason why we have this holder is to make sure that we can see how the coils are coiled. If we didn't have the holder, then you will see me draw the coils like that. Then how are you going to tell which direction it goes? You know what I'm saying? That's why we have to draw the holder, right? What happens is that most students mistake this rectangular box for soft iron core, right? It could be, but if it is, I'll tell you it is, right? If it is, I'll tell you it is. Otherwise, every time you see a coil, just assume that it's hollow on the inside. Okay, right? Right, it's a holder. Okay, doesn't matter. It actually doesn't matter here. It could be soft iron core. It could be it could be a holder. It's fine, right? But let's jump into it. So Faraday's law tells us what? Faraday's law tells us that the induced EMF, the amount of induced EMF, is directly proportional to the rate of change of magnetic flux, right? So we'll go through a few things. Okay, let's break it down a bit. What is induced EMF? What is that? It's like a new thing. The last time you induced anything was what? When do you induce? What was the last thing you did for it? Like, what do you induce? Magnetism, you induce the magnetic pole, right? Or static electricity, you induce a positive or negative charge, right? So now you have yet another induced thing, right? You induce EMF. What is EMF? What is EMF? Yeah, I mean, other than from just reading it out, what do you understand EMF to be? It is voltage, but voltage of what? When do we use the word EMF? Voltage of what? Voltage of a battery, lah, right? You wouldn't use the EMF as the voltage across a resistor, right? What's the voltage across a resistor called? What's the name for that? Potential difference, right? Yeah, potential difference, PD, correct? That's voltage across a resistor. But if it's the voltage across the battery, EMF. EMF is just voltage of a battery, right? I'm just not going to call it a battery. I'm just going to call it voltage of a source. Look at this picture. Do you see any batteries here? No batteries, huh? Okay. So the idea here is that you're trying to induce the voltage of a source. It means you're trying to create voltage. And you can create voltage when literally Faraday's law tells us that you can create voltage when there's a change of flux. When there's a change of flux. You know what I'm saying? When there's a change of flux, you can create voltage. Cannot. Right? When you change the flux, you can induce voltage. So let's look at this picture here. Is there flux again? There's flux. I'm going to push the magnet closer. Will there be a change? There will be a change. So if I were to move this magnet closer to the coil, right, there'll be a change in flux. And if this is a light bulb, so for now we use a light bulb, the light bulb will light up. So what we're trying to say here, what's the layman's understanding of it? What's the broken down understanding of it, right? You look at this definition, right, you won't understand it right off the bat, okay? What it really means is that when you do this, you're making this coil behave like a, what's that? Yeah, behave like a battery. Exactly. It behaves like a battery, right? You're creating electricity in the coil, and the coil will now behave like a battery. Is that mad? Yeah, that's mad. That's crazy. Think about that, right? You generate electricity like this. In fact, guys, this is how electricity is generated since the beginning of electricity. This is how all your electrical devices gets your electricity, right? Since, like, like when electricity was created. Okay. Right. So that's Faraday's law, and that's what Faraday's law is. Now, are you going to change the words? Are you going to go to the exam one day and decide that, oh, I want to say induce voltage? Or maybe you decide to choose induce electricity. Or maybe you think that maybe induce current is okay, what? Voltage and current, same thing, right? Guys, if it's induced EMF, don't try to change the words, right? This is not English. You don't have to paraphrase. Just leave. It's okay. Leave. Leave everything from my notes. It's okay because that's exactly how the notes is designed. It's designed, right, specifically for you to just copy down into an answer. That's the answer itself. So that you don't have to go and think about, how am I supposed to write this? Right? Just memorize the phrase. Anyway, so you do notice that I added in one word, right? It says magnetic flux linkage. Okay? Magnetic flux linkage. There is a difference between flux and flux linkage. I'm not going to make you care about it. All right. But the thing is, you have to pay attention to what your teacher is saying. Okay. Because it's kind of like school specific, teacher specific, especially for the IP school. Some teachers want you to write it. Some teachers don't want you to write it. Me personally, I'm going to tell you it's the same thing. flux and flux linkage is the same thing. However, I think Barker wants the students to write flux linkage, right? Like, if you don't write flux linkage, they'll -1 mark from you. So you must make sure that you write magnetic flux linkage. I don't know about your school. Do you see the word linkage in school? No, you don't? Then you write magnetic flux, right? That's fine. At the final exams, it's okay, right? There's no difference, okay? Right? I never heard of it to be a difference. You? Yeah, Thailand, right? Forgot. Okay, so just take note of this. Those IP schools, just make sure that does your teacher want you to write flux linkage? And some teachers may even penalize students for not writing flux linkage, right? If you just write magnetic flux. Okay? Yeah, they're just annoying that way, right? I'm not like I don't make the rules, right? So I'm just telling you how to safeguard yourself. So that's what Faraday's law says. Faraday's law says that induced EMF, the bulb will light up. Then we come to Lenz's law. Lenz's law tells us that the induced EMF and therefore the current, there will be a certain direction, right? Lenz's law talks about directions. Because you look at the coil now. Look at the coil. I know the bulb lights up. We know the bulb lights up. There's electricity running in the bulb. There's electricity running in the coil. But where is it running? Where's the direction? Is it flowing like that? Or is it flowing like this? Right? How do we know what's the direction of current? Right? So you have to understand this. Lenz's law tells us that the induced current, when it flows, it will try to oppose the change. Okay? Key phrase is oppose. Like literally use the word oppose. Don't try to use any other words like repel or rebel, you know, or I don't know, fight against. Okay? Just say oppose. But case in point, I want to make a point is that a lot of students think that the word oppose naturally means repulsion. That is not the case. Okay? Right? And a lot of students also think that oppose just means opposite poles, right? They see the word oppose. That's opposite poles, right? I see south, then it must be a south. I see north, it must be a north because I want to get repulsion. Right? Please don't think of it that way. Okay? So oppose, right, is opposing the action, opposing the change. What that means is that if there's someone, I'll draw the someone now. If there's someone who's trying to push this magnet in, the coil, upon getting its EMF, will try to oppose that action. It will try to oppose the magnet going closer. Okay, so I ask you this, what do you think the coil will try to do? What? Sorry? Like it's like, okay, imagine you are the coil. Imagine you put yourself as a coil. I'm the coil. The magnet is coming towards me. Run away. The guy cannot pick up his legs and run, right? But at most, what can the coil try to do? Try to oppose it by repelling it, right? I know I said that the opposing is not always repulsion. Okay, sometimes it could be attraction. Okay, so don't misquote me and say that oh, I thought you said opposing is not repulsion. So opposing, it can be anything as long as you try to fight against the change. Okay, try to kind of like go against the change. So if you do see a north pole coming towards you and you're the coil, what would you do to try to reject him? You will try to induce a north pole here. So that if the north pole is incoming, this coil will try to induce a north pole at this corner here, right? Sorry, I used the green one. Induce a north pole. Now this is a me thing, right? So I've always used this notation, like ever since I started teaching back in year 2007. Oh gosh. All right. I've always been using this notation. You see the small I there, right? IN, that would represent induced north pole, right? But that's just me. I've never seen any other teacher or any other textbook or any other notes use this before. So that's just me, right? I mean, I just like using, right, the induced, right, to show the induced north pole. If not, everyone will get a bit confused, right? Between, oh, is it north pole or what? So it's an induced north pole. It's induced because current is running inside the coil, right? Right? There's a north pole because there's current running inside the coil. Like, when current runs inside a coil, according to electromagnetism, this thing becomes an electromagnet, right? Okay, so the coil, someone pointed this out on Thursday, which was quite interesting. So like she was just sitting there and then she was just wondering, does this mean that the coil becomes an electromagnet at the same time it is also an induced battery? Yes. Okay, right? Because that's what it is, right? Faraday's law tells me it's the induced EMF, right? But now that there's current flowing inside, it also becomes an electromagnet. So this coil is now behaving both at the same time, an electromagnet and an induced battery, right? No, she's not wrong, right? That's great because that's where you're trying to connect the dots, right? Okay, so then you have this induced north pole here. So how do you find then, knowing that it's an induced north because you're trying to repel this north pole? How do you find the direction of induced current inside then? Yeah, good. Use your right hand grip rule, right? Because if I tell you that, oh, north pole is this way, then ask you what's the direction of current, then the first thing is right hand grip rule. The thumb must point there. Yeah, right? Because the north pole is here, bro. It's fine. I know you haven't done this in school. It's okay, right? Just get used to it a few times, right? Okay, so your thumb here like this, right? North pole like this. So the current is flowing this way, right? It's flowing this way, up and behind. Okay, so the induced current will be flowing this way. So I want everyone to draw your arrows in, trace it all the way to the bulb, trace it all the way to the bulb, and that's why the bulb lights up. And you can, and according to my notes, I would like you to label this as induced current, II. Does it make sense? Yeah. Okay. But yeah, just in case, I mean, they will never ask you to label it in a diagram. It's just me teaching you to label it so that you will recognize that it's induced current, right? So there's induced EMF, like the whole thing gets induced EMF, right? The whole coil gets induced EMF, and then the current flows because it's now acting like a battery, and then therefore it's a induced current there. Okay, this, yeah, right. So I want you to consider a few things, right? Lenz's law tells us that the current is such that it will oppose the change, right? And basically, as the magnet comes towards the coil, it will experience, like, the magnet will experience some repulsion because it's like you're trying to push the north pole towards the coil to try to reject you, right? By inducing a north pole here, so it kind of like rejects it, and by the action of doing that, right, it creates an induced current, and induced current flows in the bulb, lights up. I mean, what if you stop? Like the moment you stop, like you have a current as long as you're moving, but once you stop, right, it'll stop flowing. Okay? Because you're back to Faraday's law again. If the rate of change, that means if there's no change in the flux, then the induced EMF is also zero. Okay? Understand this, huh? Let's summarize this. So I always use a 4-step, right, description for this. Sometimes you can get a 3-mark question asking you explain why the bulb lights up, and you have to explain both Faraday's law and Lenz's law together at the same time, right? So let's go through. Let's just summarize these 4 steps here. So number one, we always must mention that the coil experiences. What does it experience first? Like, what's the first thing it experiences when you move the magnet? So the magnet moves, right? So magnet moves. Oh gosh, the sensor here is a bit bad. So the magnet moves. Okay, the magnet moves, and the coil experiences what? When the magnet moves towards the coil, what does the coil experience? What's the first thing it experiences? I mean, there is flux. There's flux, right? So, but when the magnet moves, then the coil experiences a change in flux. Okay, you see, there, right, is the most one of the most common mistakes that I get every year, because a lot of students always drop the word change. Like change in flux is literally a key phrase that you need to put in the answers. So core experiences a change in flux. Now I'm gonna shorthand this a bit. I'm just going to use a triangle sign, right? So experiences a change in flux. Number two, what do you explain next? Since it experiences a change in flux, there will be there'll be an induced EMF. Good, right? So by Faraday's law, right, the coil will have, hang on, I'll step out of the way, an induced EMF. Okay, by Faraday's law, the coil will have an induced EMF. If it's a if it's a 1 or 2 mark question, they may ask you why does the bulb light up. Then that's where you end, right? Maybe this is even with just 1 mark only. But if they ask you explain why the current flows from right to left, oh, then you have to quote Lenz's law. So the third thing that you need to quote is number 3, by Lenz's. So like oh, firstly it's a closed circuit. Okay, then there will be induced current, right? It's a closed circuit, now there will be induced current. So later on I'll show you an example where it's an open circuit and you realize that, oh, that's where it's different. So closed circuit, there'll be induced current, and by what? By Lenz's law. By Lenz's law, the direction of the induced current, which is number 4, right? So by Lenz's law, right, the direction of the induced current is such that it opposes the change in flux. Okay, so this is like the 4 steps that you always use when you're trying to describe these things. And with this, you basically understand how electricity is generated. Yeah, up to the point whereby even you realize that you even figured out being able to tell what the direction of the current will be. But we have to do many scenarios, right? Even though as simple as this basic concept is, right, there's going to be a lot of scenarios. But let me just settle a few nitty-gritty stuff first. Number one, when you push the magnet towards, I want you to imagine that you're the guy pushing the magnet now, like you're trying to push the magnet in. You apply like a pushing force here. Okay, you apply like a pushing force here. So let me draw a pushing force here. So this is the pushing force, right? This is you pushing the magnet in. As you push this magnet in, that's you, okay? You are pushing the magnet in, right? Is there a repulsion here? Is there a repulsion here? There's a repulsion here, right? North versus north, right? Induced north versus north. There's light poles, right? There will be a repulsion here. So am I right to say that you will experience some sort of like opposing force, right? So write this down as an opposing force over there. Opposing force. That means that you be able to sense this, because you will see that pushing this magnet in, has a little bit of like a resistance to it. It's not so easy to push in directly. You get what I'm saying? Right? Those who are online, I'm just gonna show you what I'm gonna do. I'm gonna pass this around, and it's to show them that when they try to turn it, it's actually not that easy to turn. It's not like a free moving thing, right? And in fact, you can even hear some noise coming out of it. Okay, what most students write about this, right? If they are asked a question on this, right, is that they'll say it's friction. It's not friction, right? Why would I create a device that has intentionally a bit more friction in the device? That's lame, right? You wouldn't create a device like that. I hope you don't, right? Don't create doorknobs that are meant to turn smoothly with friction in it, right? Why? Okay, like why would you do that? So the reason why there's like a little bit of resistance as you're pushing it, right? As you're pushing it, the light bulb lights up. Okay, right? And the reason why that you're trying to like experience this is because of the opposing force. Like there's an opposing force opposing the turning effect, right? So as you turn, it is a little bit difficult to turn. Okay, right? So yeah, feel it for yourself. I think the idea is for you to feel it, right? So there's an opposing force there. You get what I'm saying? Okay. So from a physics point of view, physics, is the guy trying to do work against this opposing force? Like when he's pushing the magnet, is he doing work against the opposing force? Is he doing work against the opposing force? I mean, he is, right? He's pushing the magnet against the opposing force. It's like you trying to do work against friction, right? Okay. So he is doing work against opposing force. So is he expending extra energy just for this to happen? Like for him to overcome the opposing force? He's expending extra energy, right? Like what sort of energy is the guy expending? Chemical potential energy, right? Okay, so chemical potential energy. So he will be using some of his chemical potential energy to do work against the opposing force. So the question is now then what happens to the chemical potential energy? Like, what does it say what? Like we are creating the battery lah. So in terms of energy, we are using our chemical potential energy to convert into electricity lah. You know, right? I mean, and that's basically it, right? That's basically it. So the idea that he's doing work against the opposing force, right? He's converting some of his own energy into electrical energy and then into light. Okay? So down here, work done against the opposing force is converted into electrical energy. That's basically it. And that is the application. That is the application of the conservation of energy. Lenz's law is an application of the conservation of energy, right? Because, right, the work done against the opposing force will be converted into electrical energy. You get it? Yeah? If you understand it, that's great. So the next thing to note is this, guys. Does the coil experience repulsion? Like, if there's a repulsion force on this North Pole, is there a repulsion force on the coil? Would there be? Yeah, there must be, right? Okay. I mean, it is an action-reaction pair, which is why they say Lenz's law is also the application of Newton's third law, right? Like if you try to repel this magnet, you yourself will get repulsion as well, right? So there you go. So there's an opposing force here as well. So in a way, if you don't hold this coil in place, right? If you don't fix it to the table, if you push your magnet towards the coil will actually shift back as well. But we usually don't care about that. Like we always assume that the coil is like fixed onto the table or like placed on a holder that doesn't allow it to move. But the coil will actually shift backwards as well, right? It's just science. It will. Yeah, it does that all the time. Okay. Yeah. Then the next thing is I'm not too sure who might be still confused about this. I hope you're not. Does these two forces cancel each other out? This is acting this way. This is acting that way. Do they cancel each other out? I think those are the cars saying no, and they are right. So these two forces don't cancel each other out, right? Action reaction pairs do not cancel each other out. In fact, why don't they cancel each other out? Because it doesn't make sense. Look at this. This opposing force is acting on what? Acting on the magnet. This opposing force acting on what? Acting on the coil. They're not the same object. How can they cancel out? It doesn't make sense, right? You want forces to cancel each other out, they must be acting on the same object. If you have one object, one force points this way, another force points that way, right? Then yeah, it can cancel each other out. But those are not action reaction pairs. Those are just opposite forces acting on an object. So if you want to talk about real action reaction pairs, it will be these two, right? This force acts on the magnet, this force acts on the coil, right? They don't cancel each other out. So if you realize that, oh shit, like I thought they cancel each other out, or I thought they are like, or you maybe you thought that on a same object, opposite forces are action reaction pairs, right? Please go and ask me for my forces videos. Okay, all right. I think I made a quite a clear picture when I teach forces, right? I can't possibly jump into forces now. I'm doing EMI. Okay, right. Okay on this so far. Can Okay, good. All right. So you understand this? I'm gonna ask you to draw. Right. I'm gonna ask you to draw another one. Right. So on your blank paper, on your blank pages, right, or your blank spaces, right, or empty papers, or your iPad, you go and create another page on your iPads. I'm gonna ask you to draw one more one more diagram. So draw together this with me. Okay, draw the exact same setup if you could, which means that the coils are the elongated S shapes. Okay, right, like this. So it's the same one as my notes, right? This diagram here. You can see these are like the big integral signs, right? Look at that, integral signs of this. Okay, right, I'm gonna ask you to draw it like this, right? So these are like the big integral signs. I just want you to get the direction of the coiling the same. Yeah, that's the thing. Okay, but this time around, I want you to pull the magnet away. I want you to pull the magnet away from the coil. I want you to pull the magnet away from the coil. I think the first thing is this. Is there a change in flux as you pull it away? What kind of change was it? Was it decrease in flux? Great, right? I mean, that's the exact phrase that you hear like an IB student saying it, right, or JC student saying it. So as you pull the magnet away, there was flux, and as you pull it away, there is no flux. So is there a change? There's a change. What's the change? Decrease. There's a decrease. So will there be an induced EMF in the coil? Yes, there will be. Faraday's law tells us that there will be, right? Have faith in it, right? These are the things I ask you to have faith in. Sorry, guys. Okay, so you pull the magnet away, right? There will be an induced EMF in the coil, right? But I'm gonna ask you this, okay? So will the bulb light up? The bulb light up. That one, everyone was like, oh yeah, I know this. I got this down, no problem. But what's the direction of the induced current? So there will be induced EMF, there's induced current, and I'm asking you to find the direction of the induced current. You can just simply tell me that, oh, it's just the opposite of just now lah. You're not wrong, but I want you to explain how. So as you pull this north pole away, what will the coil try to do? You'll try to attract it back, right? Why? Correct, because it wants to oppose the change. So what happens here is that a lot of students miss this point. They miss this idea. They completely miss this idea, thinking that opposing means that I need to repel everything. No. Right now the coil is like, hey, where's the north pole going? Can you come back, please? Because I don't want you to go. Right? Basically, the coil is always trying to oppose any action that's done to it. So it will try to induce a south pole to try to attract it back. It's like, hey, don't go away, right? So come back. It's like the coil is as if some sort of like just oppose everything type of teenager, right? Like just rebel against everything, that kind. Like, why are you coming towards me? Go away. Hey, where are you going? Come back. You know what I'm saying? Okay. Then what's the direction of current then? What do you use? Yeah, right hand grip rule. This time around, the back of your hand, back of the right hand grip rule is facing this way, right? Because you say that this is south pole, so the the chopping part of your hand will be facing the left, okay? And then you grip. So the direction of current will be going down on the wires, right? Flowing downwards on the wires. So there you go. Direction of current will be flowing. Whee! And then when you trace the current, you realize that, hey, that's a bit weird. The current is now flowing from left to right, right? So the induced current is flowing from left to right. Ooh. So tell me what happens. Oh, hang on. Is there opposing force? Is there opposing force? There is, right? So where's the opposing force acting on the magnet now? This way. Because he's trying to pull it, right? He's trying to pull it. He's trying to pull it away, right? He's trying to pull the magnet away. In fact, the fact that we know that this is south pole, the opposing force is pointing this way because I mean, this I call it F opposing, but technically speaking, what is it? It's a electromagnetic. I mean, it's a magnetic attraction. North pole, south pole, right? It's being attracted back. So does the coil experience an like a attractive force as well to the left? Yeah, it does, right? Okay. So when we call this opposing force, that's the magnetic attraction, right? Because of the opposite pole. You get what I mean? Yeah, guys. What happens if you push the magnet towards, pull it away, towards, away, towards, away, towards, away, towards, away? What's that? Change what? What the direction? Are you saying that the coil will get like that, then like this, then like that, then like this, then like that? Are you saying that? Yeah, you're right. What's that called? That's the first thing you said to me this morning. That's why I was a bit shocked when you said that they were on that chapter. I was like, what? Yeah, alternating current. If you push the magnet towards and pull it away continuously, the bulb is going to get an alternating current. Ah, so as you push and pull the magnet and you keep doing it periodically, right? That you keep doing it continuously and periodically, okay? You are going to get an alternating induced current. I'm pretty sure you all know how to draw sine waves, right? I'm not great at drawing, but I guess this will do. You will get an alternating current. And why does it? What does the? This is AC. This is AC. Okay, small points though, I need to point out because really over the years, I've had so many students who always have this kind of weird misconceptions. I don't know where is it coming from as well. I don't blame them, right? Actually, I blame their friends. Because a lot of times, right, I get students that tell me, oh my god, my friend tell me this, blind leading blind, guys. Right? You don't ask your friend. Okay? Sometimes you don't even know. Your friend might be just like, anyway. Yeah. You don't call them friends. Alternating current means the current is alternating. The voltage is also alternating, right? It's an alternating induced EMF. If you push and pull the magnet, you will get alternating induced EMF. You get what I'm saying? So AC, right, also means that there will be an alternating induced EMF. Alternating induced EMF literally means that the direction is changing. So it goes from right to left, left to right, right to the left, left to right. We don't need to define exactly which one is positive and negative, but it will go positive, negative, positive, negative, positive, negative, like this. You know what I'm saying? Like, what is the opposite of an AC? What's the opposite of an alternating current? We did this in the previous chapter. What's it called? DC. It's called direct current. And how do you create a direct current? DC, like this, right? I'm going to draw this here. Direct current. How do you draw? How do you? Yeah, it's just a battery, right? But why is it a DC? Why is it a DC? Because the direction doesn't change, right? Get it? DC. Direction does not change. It should be called DDC actually. Direction does not change. Direction doesn't change. Yeah. Okay. So in that sense, right? A bulb gets from a battery DC because the direction is constant. The direction is constant. And then the reason why this is AC is because literally, if you push the magnet towards, the current will flow from right to left. If you pull the magnet away, the current will flow from left to right. Right? If you keep on doing that, then this bulb here will be like, oh, positive, negative, positive, negative, positive, negative. Yeah? Okay, my next question will be, anyone got any questions for this? Like, do you think anything is a bit weird for this? Anyone? What? What? Oh, you try to find something. Okay, yeah. Do you think there's any, I mean, nothing wrong with the thing I'm teaching you. It's just that, is there anything weird to you? Does it strike you as like, I'm trying to appeal to your inquisitive nature? Yo, no, no, yeah, what's not working? Oh, your brain is not working. I thought you meant the bulb is not working. Right. I think the usual questions I get, right, regarding this is, really, can bulb works on AC? No, as in the filament lamp. Let's say we put a filament lamp. Can it work on AC? Why? Okay. What's inside a filament lamp? A filament, right? What's the filament made of? Yeah, tungsten. Right? It's made of tungsten, right? Is it a normal metal? It is a normal metal, guys. It's in the periodic table. It's a normal metal. You're doing all weird looks on it. It's a normal metal, tungsten, right? It's just a What's the structure of metal? Yeah, give me the whole thing lah. What? Yeah, the structure lah. Is that called giant metallic structure? Is there such a thing as called giant metallic structure? Is not thought it's just metallic. No, no, dude. Giant and simple is meant for covalent bonds only. Like giant covalent. This is just metallic. Yeah, metallic lattice is surrounded by C or D localized electrons. I don't think there's a word giant or not. I don't I don't think so, man. Really? Is that does metallic bonding come with the word giant in it? Okay, you check with Esther. I don't know. Maybe your syllabus is different. It might be a school thing. I don't know, man. Okay, so anyway, tungsten, right? Tungsten. Metallic structure is what? What's the idea of metallic structure? Wait, what? Metallic structure, dude. English. Come on, English. Tungsten. Metallic structure, chemistry. Lattice of positive ions surrounded by a sea of delocalized electrons. Goodness, guys. So you have a bunch of electrons, right? A bunch of electrons, right, like this. Okay, the current, right? If you push and pull, the current flows back and forth. Okay, what are the electrons doing? Imagine, imagine I'm the electron here. What's the electron doing? Right? He's just going left and right like this. Okay, he's just oscillating in it. But how does it get it to light up? Like, so what if the electrons are moving back and forth like that? Colliding with what? Huh? The electrons collide with each other? No lah. Yeah, collides with the positive ions, right? So it's kind of like this. Imagine this is tungsten, right? Imagine this tungsten, and then there's an electron just going back and forth like that, right? Then what happens to the ions? What happens to them? They also vibrate and start colliding with each other. What is that? What happens when atoms are vibrating? Like, what happens when atoms have increased Ke? When atoms have increased Ke, what happens? What happens? Yeah lah, it becomes hot lah. So the electrons vibrate, right? Because of the alternating current, the tungsten ions, the tungsten atoms vibrate, right? Because of the collision by the electrons. Everything becomes hot. And when tungsten becomes hot, it glows. That's the whole idea. So this thing here, everything will start vibrating, vibrating. Oh, I'm trying to draw some vibration into it. Vibration, vibration, everything vibrates, right? So the tungsten atoms vibrate more vigorously, right? Tungsten atoms vibrate more vigorously, right? It becomes hot. It starts to produce light. That's how a filament lights up on a molecular level. Do you need to know this? Hell yeah, you need to know this. How about DC though? DC is what? DC is the electrons flowing in one direction, right? You get what I'm saying? DC, the electrons flow in one direction. Does it collide into the atoms? It does, right? That's why the even for DC, even the for DC it will be something like that. Let me just draw this for you, right, very quickly. Let's say it's DC, right? So in case you're like, oh, Sam says that light bulb can only work with AC. Okay. So if it's DC, the electrons only go in one direction. They collide with the atoms. The atoms vibrate more vigorously. The heat gets hot. It lights up. Same thing, right? The only difference is that these electrons here are just moving back and forth, right? They're moving back and forth because there's an alternating current. You know what I'm saying? So the atoms still vibrate anyway. The whole point of generating light is to get the atoms to vibrate, right? That's how light is produced, right? So as long as electricity, which means electrons, are colliding into your atoms, right, because of some movement, some flow, right, it will become hot. Now tungsten is a metal that is very susceptible to getting hot very quickly, right? So tungsten is like, oh, there's a bit of current, I'm just gonna go and get hot, right? So and then afterwards it start glowing, and that's how a filament lamp works. You get what I'm saying? So it doesn't matter whether you use AC or DC, right? As long as you can get the electrons to start hitting the atoms, right, colliding with the atoms, right, the tungsten will get hot and you'll start producing light. Okay, but that's not the weird thing. I'm just trying to show you how light is produced, right? And how a bulb can work with AC anyway, right? But that's not the weird thing. Where's the weird thing, anyone? Um, the weird thing is here. That's where the weird thing is. What do those black circles mean? Huh? What? That means the current is zero, right? I mean, that's where the circles are at, right? The current is zero. Why is it zero? It's zero because you're trying to change direction. You're going from positive to negative. You got to go past zero, right? If you're not sure about that, you have to ask your math tutors. Right? How come go from positive to negative? I need to go past zero, right? What does that mean to the bulb? At one point, the bulb should go off. Right? But at one point, they should go off. You're not wrong. You're not wrong. Okay? But at one point, actually, the current is zero. So in a way, right, if you try to generate electricity, where's my oh, if you're trying to to generate electricity, and you do it very slowly like that. Look at the bulb, right? The bulb's flickering, right? Yeah, you don't want to live in the kind of environment, right? It's going to be horrible. Okay, so one thing is some of these bulbs here in my in my room, they are flickering. You can't see it. I sent out. Yeah. I sent out the video. That's the thing. The camera FPS is super high. That's the thing. Yeah, it's super high. It's 240 frames per second. The slow-mo function on an iPhone, 240 frames per second, FPS. That's why every second it takes 240 frames. You get what I'm saying? Right? The AC that we get from Singapore Power is 60 hertz. It flickers 60 times a second. So the camera is able to capture, right, the flicker. You know what I'm saying? But our eyes can't see it because our eyes cannot see anything beyond 30 hertz. Yeah, our brains are a bit slow. You know? I mean, mine may be slower than yours, but yeah. Okay? Right? Our brains are a bit slow. So that's why we can't perceive that flicker. Like to us, it looks like a continuous light source. To certain insects, though, they can see it. Right? Insects are very disoriented by fluorescent lamps. Yeah, so this is fluorescent. Now then the reason why the other bulbs are not flickering is because they are special kind of bulbs. They are LED bulbs. It's one of those like constant brightness bulbs. It's got some special device in it that doesn't take the flicker, right? It just produces constant source of light, right? It's just a special bulb. Okay, that's none of your business. Your business is to understand that bulbs do flicker, but we can't see it. Yeah, our human eyes can't see. Okay, so the next time you go and buy a Prism Plus monitor, right, and then the salesman try to show off to you and say, hey, this monitor got 240 hertz. Sorry, my brain says so what, right? I cannot perceive anything more than 30 hertz, right? Don't get bored into it lah. All right, you got a high refresh rate. That's what you built into your monitor, but my eyes can't tell the difference, right? Right? They'll probably say that, oh, but a pro gamer can. Sure, right? I'm very sure they evolved to be able to play games, right? Okay, so that's the weird thing that I was trying to get at. That's all. Okay, right? So this is how alternating current is created, and there's always going to be an opposing force as long as you keep trying to create electricity, right? You might be thinking, does it mean that the opposing force, right? The very fact that I'm creating electricity, this electricity is trying to oppose my action. Yes, because nothing comes free, what? Right? You want to generate electricity, you got to do the work, right? You want the results, you got to do the work. Get it? Okay. Anyway, so I want you to draw another diagram. So we're gonna draw one more diagram. All right, same diagram. Now you might be thinking, wow, now this Sam always ask me to draw diagrams for what, sia? All right, I'm gonna tell you this, okay? All right, go and blame Harvard for that. Right. So 5 years ago, I went to watch like a Harvard, some neuroscience, Harvard research back program kind of thing, and basically they were just saying that all your ideas of what kinesthetics lah, auditory lah, all the visual learner, all that are all BS. They're all placebo. They trick you into thinking that you can learn, and therefore you try those methods, and then suddenly, oh shit, I can learn, but it's all BS. Okay. So yeah, try reading a book on learning how to swim. Yeah, right. Okay, so my point is you got to use all types of learning styles. Okay, I'm not saying that you don't have a preference. You probably have a preference, but anyway, the neuroscience research shows that your preference is also probably wrong. But anyway, you got to use all learning styles. You need to use hands-on. You need to use auditory. You need to use visual. Right, same everything. Okay, and Harvard says that the best way for students to learn is to draw and write. So I'm making you draw. So if anything, blame Harvard. Go and write a letter to them. Go and tell them that hey, my tutor makes me draw all these diagrams, right? Okay, and it's all because of your fault, right? Can you please redact that statement? Can you take away that research, right? It's making my life hell, man. Why do I have to draw another magnet, right? I have to draw another coil. Gosh, dude, Harvard, what the hell? Okay, this time around I put a voltmeter. Okay, I push the magnet towards the coil. right? It's a voltmeter. Voltmeter reads what? Voltage, right? So when you push the magnet to the coil will get change in flux, Faraday's law, induced EMF, right? So will there be a deflection in the voltmeter? Will there be a deflection in the voltmeter? Why do I have to think? Sam, just tell me the answer lah. Can lah. Can, I can just tell you the answer. Then you're not thinking, oh, what? Will there be a voltmeter reading? Will there be a deflection in the voltmeter? Yeah, there will be, right? There will be a deflection in the voltmeter, right? Yeah, I'll talk about the magnitude later, right? I'll tell you that the voltmeter will have a deflection. Okay, the voltmeter will have a deflection. Okay, because it's induced EMF, right? So let me write that down. There's induced EMF, and therefore there will be a deflection. So I write a deflection, and I put a tick to there, right? Deflection. Okay, so there will be a deflection. Will there be an induced current though? Will there be induced current? Why not? You see, the voltmeter is right smack in the middle of the circuit, right? Right, indeed, right? There's no induced current. Okay, there's no induced current because the resistance of this voltmeter is infinite. So unfortunately, you place it in such a way that the voltmeter is sitting right smack in the middle of the circuit, right? Even if you have induced EMF, it's not going to have a current at all. So question is this: will there be an opposing force? I use green colors, right? So will there be an opposing force? No. No opposing force. Okay? Because here's the idea. How was the opposing force created? Because there was an opposing pole, right? How was the opposing pole created? Because there was an induced current, right? Electromagnetism, right hand grip rule tells us so. So if there's no current, then there's no induced pole. No induced pole, there's no opposing force. So here's the thing. Listen very carefully. You can get induced EMF, but you may not get induced current, right? So if like so some people will be very very confused at this point. I thought voltage is like electrical energy. So if this guy is pushing it, would it be so? Voltage itself is not electrical energy. Voltage is the potential for current to flow. That's why it's called potential. That's why voltage is called potential. Like the word potential is to suggest to you that it potentially can flow, right? But if it's an open circuit, if it's a block circuit, no, it won't flow. Okay, so you can get induced EMF but no induced current. You're not actually generating electricity. There's no electrical flow, electrical current flow, right? There's no opposing force. This guy will just push this magnet in very very easily, but there will be a deflection. Okay, so voltage and current are two different things. That's what I'm trying to get at. Okay, all right, good. This would be the like the wrap up of all these things here, right? So take down the notes if you have to, right? Let's take a well, actually I don't have much time for a quick break. Okay, don't much time for a break. So once you copied this down, right, just get yourself ready in 3, 2, 1. Okay, good. So a big major part after you learn the basics, and that these basics will apply to almost every other page in this set of notes. Okay, a big major part of what you need to know, right, are the different scenarios. Again, this chapter has no equations, has no calculations. Okay, but your job is to investigate all the scenarios that you can. Right. So we start off with this one first. Right. We have this scenario. We have a magnet that's going to fall through a coil. It's going to fall through the hollow of a coil. So I have a coil, right? I have a coil, right? I face it this way, right? This way like that. And then I let a magnet fall through it like this, right? You get what I'm saying? But this coil is kind of long. It's a kind of long coil, and it's connected to a galvanometer. Right? Write it down. Galvanometer is a G meter. Oh, it's a galvanometer. Right? Galvanometer. What's a galvanometer? Ammeter. It's a very sensitive ammeter, right? It's a sensitive ammeter. Why do I make a difference? Like, so what if it's a voltmeter or ammeter? What's the difference? Yeah. What was the other big difference that you just learned? If I connect a galvanometer there, exactly. So this galvanometer has no resistance, which means that induced current can flow. Ah, okay. And that's what's going to happen here. So as this magnet is falling towards the coil, right? You see this magnet is falling, 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 and falling towards the coil. Will the coil try to do anything? What would it do? How? Let's just jump the four steps. You already know the four steps. If I repeat the four steps all the time, right? I think my tongue can just fall off. What? How? Inducing what? So there'll be an induced north pole at the top here. Okay? At the first part, as the magnet is falling towards the coil, right? The coil will induce the north pole. Direction of current? Yeah, right hand grip rule. Okay? Direction of current will be this way. I mean, I'm jumping all the steps. 1, 2, 3, 4. So 1, 2, 3, 4. Right? If you need to refer to the previous page, I asked you to write down 1, 2, 3, 4 already, what, right? Right. That's why, you see? Right? I make my life easy. So that will induce north. Right hand grip rule. Induced current will flow this way. This is the induced current. So draw it on the left hand side first, right? Because I'm gonna ask you this. Okay. So now this magnet is gonna fall, 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 fall. It's gonna fall through. It's gonna fall away. Right? It's gonna start falling, 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 and it's gonna fall out of it. Okay? It's gonna fall out of it. Then on the way out, as it's falling away, right, the coil will then notice that, hey, the south pole is going away. So what will the coil try to do? By how? Where? So you're telling me that as the magnet falls through and falls past the coil and falls away, right? On the second half of the fall, this coil will induce a north pole at the bottom to try to pull it back up. Absolutely right. There will be an induced north pole at the bottom, right? So it kind of like the current will change direction. So the induced current will be like this. Yeah, you get it right. Can lah, can lah. But hang on, What does this mean for the magnet? Does it experience a opposing force here? Does it experience an opposing force here? So what's the direction of the opposing force? Why you shake your head? Why? What? Were you shaking your head or nodding your head? Nodding. Okay. Where's the direction of opposing force as it's falling? Upwards. So there will be an opposing force pointing this way. I mean, strictly speaking, what's this opposing force? It's a repulsion, right? North pole repel North pole, right? It's opposing force. How about when the magnet is falling away? Where's the direction of opposing force? Upwards. But what kind of force is it? It's an attraction. So opposing force doesn't mean attraction or repulsion. Let me say that one more time. Opposing force is opposing the action, right? It could be repulsion. It could be attraction. Okay. So are you telling me that as the magnet is falling, it's experiencing some sort of opposing force? I mean, what happens if the magnet is just falling without the coil? Let's say I have another magnet here, like this. If I had another magnet here, north south, and it's falling, like how would it be falling? Yes. Yeah, it'll fall with G. Right? If it's a free falling magnet with no air resistance, this magnet is gonna fall with G. Like what is G? How much is G? 10 meters per second squared. Right? It's gonna fall with this acceleration, all right? Except for some of the IP ones, you have to do 9.81. Yeah, I know, right? Yeah. 10, right? 10, right? Yeah. I mean, NGS IP is 9.81. Okay, so 10 meters per second squared. Then you just standardize it. Like, why do you make life so difficult? Okay lah, it's fine. I still can play around, right? Yeah, doesn't matter to me. I'm still good at what I'm doing. So what's the difference between the two? Like this magnet falls because of its weight. Like what's the only force that's acting on the magnet when it's free falling? It's its weight, right? It's like this mg, right? Right, mg is his ma, right? That's why the a is the g, right? Like mg is the resultant force. But how about for this magnet? What's the resultant force of this on this magnet? It will be mg minus the opposing force equals to ma, right? You see that? Mg minus the opposing force equals to ma. So what happens to the acceleration of this magnet? Less than 9.81, less than 10, right? Right or not? Okay. So I know there's no visual now. I'm asking you, can you imagine how does this magnet fall compared to this one? Yeah, fall slower, right? Okay, no, but there is a demonstration. So what I have here is a copper tube, right? It's a copper tube is non-magnetic. This is a magnet, right? So I'm first gonna just drop it like that. So if I drop it like this, you can see how far it falls, how fast it falls, right? So it's something like this. Yeah. Sorry. Don't know why I can't catch it. My hands are not coordinated. Anyway, so yeah, so that's the rate at which it falls, right? So what happens when I drop it through the tube? It's a hollow tube, right? It's a hollow tube, okay? Right, and then I let it fall like this, right? So it takes a lot longer to fall through, okay? This, yeah. So I will have time to like do a wave and then catch it at the bottom. Okay, so that's the whole idea. So this tube here that you see, right, is acting like this coil, right? So yes, some people will be like, oh, does this mean that there's an induced current inside this tube, right? Because it's a solid tube, right? So the current can flow. Yeah, there is an induced current, but it's pretty small, so I don't feel it, right? It's not like that sort of thing, right? I'm not gonna get that, right? So one more time, so like this, so there's a induced current, and it switches, right? So at the top half is like this, and the bottom half is like that. Okay, when the magnet is falling at the top half, the induced current is probably going this way, right? Or maybe this way. I don't know which side. I don't know which side of this magnet is north or south. Actually, I don't know. So it would like either be this way or this way, right? When the current is when the magnet is falling, and then at the bottom it'll switch over. So if it starts with this, right, on the other half it'll switch to this, right? Exactly what's happening here, right? it starts with this and then it switches to this because it's trying to pull the magnet up again. Okay. Or if it starts with like that, right? Starts like this, that means the south is facing it at first. Then by the time it comes out, right, then the induced current will be like this way, like this. Okay? Right? So this is the thing you can pass around. Don't let the magnet touch your phone because it's a very strong magnet. But you can try it yourself. Yeah. Okay, let's we're gonna try to finish off with one last diagram. So I'm gonna have to ask you to draw another diagram. Yeah, sometimes you get stuck because of the holes there. So you kind of like have to keep the thing vertical. Yeah, there you go. Yeah, 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 yeah. That's right. Okay. One last diagram. I'm gonna have to ask you guys to draw this one last diagram for today. Okay. So I'm showing you a similar concept to this thing here, but this time around, there's only one coil. It's a very simple setup. It's just a single coil like that. Right? It's a single coil like this. One coil, one coil. And I'm gonna take a magnet and I'm gonna drop it through the coil, right? So it's gonna do, and then fall through the coil, like this. Okay, like that. So it's gonna fall through the coil, like that. Okay, one coil. And I'm gonna connect it to a voltmeter. So I'm gonna connect it to a voltmeter like this. Right, there'll be a voltmeter. Right, gonna connect it to a voltmeter like that. Okay. So the reason why I want you to draw one coil only is because I want you to understand that, right? This one, the opposing force is negligible. Right? The opposing force is negligible. So which means that this magnet will just fall straight through at G. You know what I'm saying? Like it's like this magnet will not have that slower movement like the one that you are seeing right now, right? It wouldn't like fall slowly, right? So this one here, the acceleration will be G. Okay, so the acceleration is 10 meters per second squared. So I'm telling you, I'm not asking you to guess, right? So I'm telling you that it will basically accelerate. So do you understand that this magnet in this particular case gets faster and faster as it's falling? You understand that point, right? It gets faster and faster. The acceleration is constant, but the velocity is increasing, so it gets faster. So I want to see the graph. I want you to draw the graph of its voltage. Right? I want to draw the voltage time graph. Okay? I want to draw the voltage time graph. Right? Okay. Now they're not going to ask you to draw the graph in the exam. I'm making you draw it so that you recognize what you're doing. But before you draw the graph, see how I draw it first. Okay, so the graph will kind of like look like this, right? So what are some of the details that I want you to pay attention to? Number one, right, there is a this side here is a bit like you can make it significantly wider than that like if you want to compared to the second part, right? The second part is like this part here. The height of the peak here is going to be shorter than the second one. The second one is going to be like a lot more, right? It's going to be a lot more greater peak like this, right? So yeah, there you go. Yeah, that's the two features I want you to pay attention to. That's pretty much it. Yeah. Okay. So of course the question will be, why is it like that? Why is this peak, right? I'm gonna ask you a couple of questions. Why is this peak like lesser in magnitude than the bottom peak? What? Sorry, what? So you're saying that, I mean, okay, whatever it is, I mean, don't use the word slower because you would make the reader think that, are you saying that it's slowing down? Right? It's not, right? What you meant is this part here is slower than the second part, right? So you can say that the magnet is accelerating, and therefore the second peak has a greater induced EMF than the first peak. But why though? How come? I mean, faster, so what? what does falling faster have anything to do with the voltage or the EMF? Yeah. What does what does falling faster have anything to do with the induced EMF? Basically, back to Faraday's law again. So if you look at Faraday's law says what? The magnitude of induced EMF is proportional to the rate of change. So Faraday's law has sort of like two parts to it. One, you understand that there's induced EMF when there's a change in flux. The other part is understanding that the amount of induced EMF that you get is based on the rate of change. So if the magnet is falling faster, isn't that a greater rate of change? It is, right? It's a greater rate of change. So if you have a greater rate of change, the induced EMF will be greater, right? So the induced EMF is greater because the magnet V has increased and the magnet's velocity has increased and has a greater rate of change of flux on the coil. Okay? Right. I think whatever it is, I still want you to remember that the change of flux is what the coil experiences. Now, some of you might be thinking like, oh, how is this greater? It's very negative. Why is it greater? How can a negative number be greater than a positive number? You get what I'm saying? Right? But that's math that you're thinking of. In physics, right? What's minimum? In physics, when I say, oh, the car has minimum velocity, what does that mean? The car has minimum velocity. Yeah, it means zero. You get what I'm saying? So being negative, like a large magnitude negative number does not mean minimum. You get what I'm saying? Minimum in physics is zero. Okay, right? Don't think of it as math, right? But then the next question will be this. So why is it positive and why is it negative? So why does it go from positive to negative? Like how come the induced EMF goes from positive to negative? Can EMF be positive, negative? Can voltage be positive, negative? Do you have positive and negative parts of your battery? I think you do, right? You do, right? Yeah. So the idea of voltage being positive and negative is just about like which direction you're facing. That's pretty much it. I mean, look at this. Okay, let me show you this. Okay. Now look at this. Is this positive or negative? Actually, I don't know. Doesn't matter, right? We don't know whether this is positive or negative. You get what I'm saying? But if I flip the battery around, if I flip the battery around like that, right? Look at this. I flip the battery around. Is it the opposite direction of this one? It is, right? So if this I consider this as positive, then that one will be negative, lah, right? And it kind of like does like does both ways, right? So the idea here is that the induced EMF in this coil goes from positive to negative because if there was a current, I mean there will be a current, but it's just that because it's one coil, so the opposing force is negligible. The induced EMF is firstly this direction, as it's falling towards is this direction, and then as it's falling away is the opposite direction. You know what I'm saying? That's why it goes from positive and it goes to negative. Right? And the negative portion, the part that's falling away, right, has a higher induced EMF because it's falling faster. Right? It's getting faster and faster and faster and faster and faster. The rate of change is getting higher and higher and higher. The induced EMF will be bigger on the second half. Okay? So a few details about this drawing. Some of you might be wondering, like, oh, is this point the point whereby it crosses the coil halfway, right in between? Yes, right. That point there is when the magnet is right smack in the middle of the coil and it's falling past it, right? Imagine a slow-mo video in your head. Okay, I can't do this for you, so you gotta have to try to visualize it in your head like this. like right at the point here like this, that's zero voltage there. You know what I'm saying? It's changing direction now, right? It's changing direction now. Okay. Some students might be asking, so if let's say we don't exactly know where is positive, which direction is positive, it doesn't matter because voltage is not a vector, by the way. Even though direction is changing, it's only two ways only. It's not a vector. Okay, it's either left to right or right to left, right? If we don't know what is positive or negative, right? So is there a chance for me to draw this coil the other way around? Can I draw it this way around? Can I draw it the other way around? Can I draw it like that? Yes, you can. You can draw it like this. If you decide that this side is positive and then the other side is negative, or like whichever way, it doesn't matter. You know, this is also okay. But you cannot draw it like that. Ah, this would be absolutely wrong, right? If you draw it like this, right, then you're just saying that you don't care where the direction of the induced EMF is. Like you only care about the magnitude, right? The induced EMF, the induced current should be a thing for you to care about. All right, so you can't draw it like this. So you have to draw it like that. Okay, or maybe even like the other one that I showed you just now. But yeah, anyway. Okay, so one more thing to take note of, last one for today will be this, right? Just last thing here, just make sure that T1 is greater than T2 lah, right? The idea here is to show that the time taken for the second half is faster than the first half because it is accelerating. It's still accelerating. It's not slowing down. This is not like the long tube, right? Where the opposing force has time to act on the magnet, so therefore it slows down as it falls, right? It doesn't. There's a negligible force, right? Negligible opposing force. Okay, we good? Yeah. So keep in mind all this. Next week I will go through all the other scenarios, right? Like next week will be a little bit more mind-boggling. Next week we'll end off with AC generator, okay? And then if I can reach here by next week, then we can start doing nuclear on the week after. But the thing is, I want. Okay, so next week the paper is not due for you all, right? But the week after, then we have to start. You all have to start, doing the questions ready, right? I just sent the message out. I realized that the message wasn't sent out, right? So the message is 2024 Nanhua High Secondary paper one will be due on the week starting 14 July. So for you guys, that paper one will be due on the 20th of July, 2 weeks from now. Okay. But for Alvin, I think you have a lot more to do before the 15th of July when I see you, right? So you have to get all the practices done within this coming week. Then we can make use of your time fully. Um, if you plan to do papers on 15 and you want to see me on 16 instead, I think that can be done. It's either 16 or 17, right, Alvin? Sorry, what? I can't hear you. Sorry. I'm sorry, I can't hear you. What was it again? So what does that mean? That means that you can only see me on the 17th? Or what time does your O level end on the 16th? That means you have to do the papers beforehand. 15, I don't see you because you should be preparing for your O levels oral. Then after your O level oral on the 16th itself, is that what you're saying? Sure. Okay, that's fine. Then can you get two full papers prepared by before then? Right. So paper one, paper two from one school, paper one, paper two from another school. Doesn't matter which one you do. I want you to at least finish up at least two paper ones and two paper twos. Right. Even if it's your past school year papers, it's fine. Okay. Thanks. Bye. Those are online. Bye. Those are here. Bye bye.